So he is going to present now the winning model or any insight she had when working on a Kaggle competition that was also co-organized by the society. Ailey is based in California. She's working for Prips. One second. For which company are you working again? I forget the name now.
Yeah, the short name is Prism.
Prism. Can you talk more about this company, because we might not be.
Yeah, sure. Yes, I will give a short introduction.
Okay. So yeah, and I wanted to add something regarding regarding your background. Can you shortly introduce yourself? So
sure.
Maybe it's better if you do that, and then you can move on with the presentation.
Yeah, sounds good. I can do that. Do you want me to share my screen and get started?
Yes. Can.
Okay, sounds good. Share. All right, thank you for joining, everyone. So a little bit about myself. My name is Yi. I probably have the shortest name in the world. And I am senior data scientist at Prism. So basically, we are one of the largest risk management pools in California, United States, and we provide primary and access coverage for public entities across the country. And then outside of the work, I am also a blogger on various data science platforms where I basically share everything about data science and my programming tips and tricks. So for my talk today, I will start with an overview of this actuarial loss prediction Kaggle competition. And then we will move on to the exploratory data analysis and feature engineering, and followed by the specific model methodologies that won this competition. And then on top of that, I will also share things that I tried but didn't really end up working, and some of my thoughts about the future explorations. So as you can see, my talk is really organized as a data science project where I will spend less time talking about the specific findings from this competition, but rather I will focus more on how I went about it. So basically walking you through my thought process and the steps that took me to my final winning model. So my hope really is to give you guys some inspiration to try something really outside of the box in your own actuarial work, which to me is more value added than purely model findings themselves. So first, let's look at some details about this competition. So the goal really is to predict workers' compensation claim cost with a highly realistic synthetic data. So for our training set, we have 54 total claims. And then for the testing set, we have 36,000. And in total, we have 14 variables as predictors, which I will go through in a minute. So when it comes to the model evaluation metric, that's everyone's favorite, which is the root mean square error. As we can see defined by this formula where the yi here is the observed value and the yi hat is the predictive value. Moving on, so now here is a sample data set showing the 14 variables that we are going to play around with. So as we can see, these are pretty typical data we would get for regular workers' comp claims, such as age or date of loss, or like hourly hours worked per week. So these are pretty standard data set. And then, as always, the first step when we analyze a data set is to do the sanity check, right? And this includes first, let's check duplicated records, which is none in our current data set. And then the next one is missing data handling. So we do have one variable, marital status, that has missing values in them. So basically what I did is I assigned a new value unknown to those missing data. And if we compare this unknown population to the previous, to the other values that are in our data, we can see that the median and mean values are significantly higher for the unknown population. And then when it comes to outlier handling, we do have one claim which cost $4 million in the ultimate incurred loss. So what I did is I basically kept it to 1 million. As we can see, the data is fairly clean. So the next step is to look at the distributions of the variables we have. So here shows all the some of the variables in here. So some are coded as integers like dependent children, and some are coded as continuous numeric variables. And also we can see that the ranges of these variables really differ significantly. So from this, it basically tells us that we need to standardize these variables before we include them into the modeling process. And I know we have talked about this in the previous presentation. So as compared to the traditional linear regression model or GLM, you probably know that machine learning, especially trait-based or deep learning algorithms, are pretty robust to skew the distributions of the predictors. And we could probably get away with not doing any transformations to the data. However, when we really look at the distributions of these two incurred variables, they are severely right skewed. So intuitively, I use log transformation to address this skewness, and this log transformed ultimate loss was actually used as the target variable in my model. And now moving on to the feature engineering. So with the 14 variable in our data set, we can derive additional variables to include in the model as well. So some of the key features include the integer part of our claim number, and then the year and month of the accident, and year the claim reported, and then the report delay, and finally the hourly wage, which is derived from the weekly wage. Okay, so here shows the zero autocorrelations among all the variables. Hopefully this is not too small for you guys to see, but I really want to direct your attention to the variables in this blue box in the middle. So for example, the hourly wage, the claim number, integer, and year of accident. So these variables appear to have some sort of moderate correlations with the incurred variables in our data, which basically means that they might be good indicators. And on top of that, so what information do we get from this correlation matrix, right? Well, the first thing is there is multicollinearity among these variables because some of them are linearly transformed from others, right? But is this concerning? Well, generally speaking, in my experience, machine learning algorithms can make use of highly correlated features, and that's actually one of the advantages of these algorithms over the traditional, say, regression models. And then another advantage is their capability of handling interactions. So based on the correlation here, we don't really see any single variable having very high correlations with our target variable. So this basically indicates that there may be some sort of interactions that have higher predictive power. So this may be two-way, three-way, or even higher, right? And then trait-based models do inherently kind of model this nonlinear relationships among the variables. So all of this suggests that maybe more advanced algorithms other than the traditional regression models might outperform for this particular data set. And now I want to say we've got most of the variables taken care of, and except for one, and that is claims notes. So how do we go about it? Because we can't really include them directly into the model or use dummy coding, right? We have to figure out a way to basically convert them to numeric vectors so that they can be fed into our model. And here as the first step, and this to me is where your actuarial judgment comes into play. You may already notice that this data set is lacking some important variables to determine ultimate loss, for example, body parts or cause of loss, right? So this information can be extracted from the notes by using the keyword searching. So on the screen here shows several examples. And the first note reads, slipped on wet floor, fractured base of hand. So from here, we know, oh yeah, so the body part is hand, and then the cause of loss is slip. So basically, by using this kind of searching algorithm, we can pull those keywords out of the notes. And then in addition, if nothing really returns from our keyword searching our algorithm, and that's okay. We can just label it as unknown, as we can see in the notes here. And now with all this keyword searching algorithm in place, all we need to do is to basically iterate the algorithm through and extract the body parts or symptoms along with cause of loss from each claim note. And we got the following. So for unique, for body part, we have 44 unique values. And for cause of injury, we have 78. I know that this is definitely not perfect by any means, but that's okay. So we will see how we can convert them into numeric vectors to be consumable by our model downstream. So one of the strategies is one-hot encoding, which works if we don't have a whole lot of unique values. However, this doesn't seem to be a good solution for this exercise because for example, cost of loss, we have 78 values. With one-hot encoding, each value will be mapped to a vector of 78 integers, with 77 being 0. So this is definitely not very kind of inefficient. So if that's the case, then what should we do? Well, in order to reduce the dimensionality of categorical variable, we can implement a technique called entity embedding, which I will briefly go through the basic idea. So formally, an embedding is nothing but a mapping of a categorical variable into an n-dimensional space. Well, that's simple, right? But how do we determine this mapping, right? In a nutshell, we build one neural network model using each categorical variable to predict our ultimate loss and find the corresponding weights. So in my model, I used one layer neural nets in addition to the embedding layer. So one of the biggest advantages of entity embedding is that it can map related values closer together in the embedding space, and therefore it can basically reveal the inherent granularity of the data. So to give you one simple example, here on the screen shows some arbitrary vectors for each body parts or symptoms. So for example, head is represented by a vector of 0.4, negative 0.3, 0.6, and 0.1. So now let's assume that the cost of a head claim is more similar to the cost of a concussion claim than to a shoulder claim, right? So using entity embedding, this relationship will be captured. Meaning, if we take these vectors and position them in a 4-dimensional space, then the position for head will be closer to the position for concussion. So if this is a little hard to digest, we can think of this idea similar to the latent factors in principal component analysis. So basically, entity embedding has been shown to work very successfully when fitting a neural net. But the weights or these vectors can also be extracted for other algorithms downstream. And that's what I did for my model. And now let's finish off our feature engineering by creating a binary variable out of the anchored variable. And I just label it as severity. And then we also standardize our variables before include them into the model. Now, because we have add more values, add more features along with the embedding vectors. So we basically increase the complexity of the model, and this will make our model prone to overfitting. I know this concept has been talked multiple times. So we basically need to use regularization techniques to prevent overfitting, and cross-validation is one of them. So I will briefly talk about it in the next slides. And when it comes to model tuning, aka choosing a set of optimal hyperparameters, what I use is called the Bayesian optimization method. So for the time being, I will skip all the technical nitty-gritty about this method, but at a super high level, Bayesian optimization is basically applying the trusted Bayesian rule to hyperparameter tuning, where the next hyperparameter configuration learns from the previous one. So this way, with each passing round, our model trains with a better hyperparameter combination in reducing prediction error. So that's why this method is also referred to as informed tuning. So that's the basic idea behind this method. And so here comes the cross-validation technique to prevent overfitting. And again, this has been mentioned multiple times, but just in case you are not familiar, so the basic steps are, we first split our training data into subsets. So here I separate them into 10 folds. And then we build 10 different models using all the subset except for one. And then we test each model against the last subset we just saved to get the model performance scores. And finally, these scores are averaged to get the final performance for the model. So basically, cross-validation works universally, regardless of the specific modeling algorithms. And when it comes to the model methodology I used, it was a stacking model with 2 gradient boosting trees. And then, so here, I want to briefly touch on like the family of gradient boosting machines. Basically, GBM trains many models in a sequential manner, where we kind of consecutively fit new models to reduce the prediction error from the previous one. And as a result of that, it provides a more accurate estimate of our target variable. So as we can see in this graph, if you are not familiar, we basically fit the first learner, the M0 model, and then we calculate the error of our prediction, which is y minus y prime here. And so this is called the pseudo residuals. And then we basically fit the next model against these residuals. And we kind of iterate through these steps until coverage or the maximum iterations is received. So as we can see, GBM is a really cool algorithm because it can provide really accurate prediction, but it suffers from several cons. So the first and the biggest one is it tends to overfit, because our next model is to build to reduce the errors. So technically, we can keep going the tree until our error is 0 on the training set. However, this model will perform really bad on the testing set. So that means regularization techniques are crucial. And then the next con is the vanilla implementation of GBM can be really slow. So that means we need like some sort of multi-core processing in order to speed up the training process. So this brings us to the two improved implementations that factor in both multi-core processing and regularization. So these are two are like GBM and XGBoost. I know, again, so these are pretty popular kind of algorithms for all the computations. So here for your reference shows a comparison of some implementation details for these two algorithms, and I will skip the details here. And now we know GBM, we know the implementations, and then the stacking model idea is just a simple weighted average. So I use the greedy search to find the corresponding weight, and turns out the 0.85 times like GBM and 0.15 times XGBoost worked the best for my model. So that's what I used for the final submission. And now let's go through the feature importance for good measure. So here it's worth mentioning that these two implementations actually use different methods to calculate feature importance. So the values here on the screen on the x-axis really are different. However, what's important here is the relative value of one variable against all the others. So for example, as compared to year of accident, the severity indicator contributes more according to the XGBoost model. As we can see, the initial incurred cost, body part, and cause of loss, entity, encoding, and also severity seem to be identified as significant predictors for our ultimate loss. And now let's talk about things that only worked for the private leaderboard. If you're not familiar with Kaggle terms, so basically public leaderboard is when after you train your model, you run it against the public testing data set, and then you get error value, and then you tune your model accordingly. But for private leaderboard, that's when all the competitions is closed and all the submitted models will be tested and evaluated against this never seen before data set. So the prediction coming out of this data set determines the final standing. So for the private leaderboard, what works is an kind of ensemble model where I build a Lasso regression model taking in all the input features to predict the ultimate loss. And then this predicted vector was treated as a meta feature to add to the original input features X. Then I took the whole data set and fed it into the two base learners as is shown in this graph here. And in addition to ensemble, I also tried more derived features, for example, cutting initial incur loss into different buckets, as well as calculating, so I call it incurred per payroll. So seems like all of these appear to help for the final testing scores. And then moving on from things that worked, let's talk about things that did not work. So the first one regards claims notes. To analyze that, I also tried LDA to perform topic modeling. So this is basically the same idea as entity embedding, where we try to find different latent topics within the claims notes and organize each note based on the topics. I also tried frequency encoding, which basically is to calculate how many times a certain body part appears. And then more derived variables, I also tried deep learning neural nets, but seems like none of them worked out. So, well, moving on, some of the final thoughts I have. So basically, there's no evaluation date in our data set. So we can't really calculate claim age from here, but intuitively, it makes sense that as claims age, they tend to cost more. So I think it would be interesting to explore the potential importance of claim age in predicting the ultimate loss. And then along the similar lines, I know the traditional actuarial analysis relies on loss triangles. Because we don't have evaluation data, we wouldn't calculate calculate the loss triangles. But it would be great if we can see like how can we incorporate the triangles into our model. And the next one is, as you may remember, our current objective function is MSE or RMSE, which is kind of a popular objective function for models. But when it comes to actuarial study, we know that there are other distributions like gamma or Tweety that might work. So it would be interesting to explore more opportunities there. And with that, it concludes my presentation for today. So yeah, thank you for joining, and I will pass the ball back to Frederick.
Thank you, Hailey, for your great presentation, showing all your exploration and methodology when coming out with a winning model.